In this video, we'll be looking into the important topics of fifth module, that is transaction processing and concurrency control. So if you have not watched my previous video, I have uploaded all the important questions module wise. So do watch that. So as an extension to that, I'll be discussing the answers here, the important topics here. So first we have the transaction, definition of transaction and read-write operations. So an executing program that forms a logical unit of database processing is termed as transaction. So it could be it could include any operation like insertion or deletion or updating a particular value or attributes or retrieval of data. So in an application program, by explicitly specifying the begin and the end of transaction, we define the boundaries. So we make use of two statements, that is to begin and to end the transaction. So they are used to define the boundaries. So the basic database access operations that a transaction can include are read and write. So these two are pretty important. By the name itself, we can understand read. Item X says that we need to read a database item X into the program variable. So here we are considering that the variable is also considered as X here. And here write item X. So write the value of program variable X into database item named X. So this was about read write. So transaction has two major operations, that is read and write. So here is the transaction, the state diagram here. So there are 4 states, 1, 2, 3, 4, begin, read write, end, commit and rollback, 5 states, sorry. So here we start at the begin state, we begin the transaction and then it reaches to the active state. So once it reaches to the active state, it has two options now, either to read or write. So read write definition we have understood. So if the read write operations are done, so connect committed transaction. Now there are further two options. It could either commit or if this transaction is further successfully completed, then it moves to the committed part. If not, it reaches to the failed part. Here, if the transaction has aborted, then it goes to the failed part, and from the failed part it goes to the terminated part. Even if the transaction is committed and completed, it again moves to the terminated part. So we begin the transaction. Read write are the two operations which we use here. End is used to depict the end of that particular transaction. Commit signals a successful end of transaction so that any updates executed can be safely committed and will not be undone. So that was about commit. And then we have rollback. If the signals that do not end successfully, in this case abort case, then the changes made must be undone. So whatever the changes you had made during the transaction need not be saved. Okay, so that's what rollback defines. So this was about transactions and read-write operations. Next, we'll be looking into the asset properties. So those are also called as desirable properties of transactions. So this could be asked for 2 marks or 3 marks, it depends. So firstly, we have for A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. So by the definition, atomicity, it says that all the operations should take place at once. If not, the transaction is aborted. So each transaction is treated as a unit. If there are only two possibilities, either the unit will complete its transaction successfully or it will not execute at all. That's what atomicity says. Then we have consistency. So whatever the constraints were there before the transaction and the constraints after the transaction should be maintained. So integrity constraints should be maintained in the transaction. So that database is consistent before and after transaction. So during the execution, prior stable state and next after the execution, new stable state should be both the states should be stable. That's what consistency states. Then we have isolation. So when a particular transaction is being executed, it has to be isolated. No other transaction can intervene the particular ongoing transaction. Not only the transaction, it can't make use of the resources also here. The data can't be used by any other transaction here. So this was about isolation. Durability is in a certain time transaction execution should be completed. If not, the changes are lost, it is inconsistent. Like when you visit ATM, there is to complete the particular transaction, when you put the card, get money, it has to complete in a particular duration. If not, you lose your money and then the transaction is all the changes are lost, right? So that's what durability states. So all these properties are important and they are desirable for transactions to take place. So this was about asset properties. Now we'll look into concurrency control. So why concurrency control is important? So several problems occur when concurrent transactions are executed in uncontrollable manner. So let us take two transactions here, T1 and T2. So two transactions are taking place simultaneously or concurrently, T1 and T2. We know that R stands for read and W stands for write, right? So first we'll read A, and then we'll perform an operation that is A is equal to, we'll add 100 to it, and then write A. And then similarly here also read B, B is equal to B minus 100, write B. So during in the single system, these transactions happen first, and then these transactions happen. But then coming to multi systems here, we may there is a topic of concurrent executions, right? Concurrent execution of transactions, right? So T1 will execute as well as T2 will also execute at the same time. So that's what concurrent transactions mean. So when concurrent transactions occur, transactions are executed in uncontrollable manner, it leads to several problems. By those problems, there could be errors, and the data could be lost, or there could be inconsistencies in the data. So concurrency control manages the access to data by many users. It manages running simultaneous applications at once. So consider T1 and T2 be the two transactions which are running simultaneously. So these would be managed and maintained by the concurrency control. So assume two users are trying to update bank account balance concurrently. Without proper concurrency control, one's update might be overwritten or erase the value. So there would be incorrect bank account balance, right? So that was an example. We'll look into this particular transaction. So if you see, first A is read, and then one operation is performed here, and then A value is written back, committed back, right? So after completion, it is committed back. Then B is read, and similarly B operations are being performed here. Concurrently, similarly, if A data is being addressed here also A data is being utilized. So simultaneously on both the transactions, A is being utilized, right? So here A is equal to A minus 500, and here write of A. So there could be problems arising when we have such situation, concurrent transactions. So we'll look into those problems one by one. So the first problem is lost update. So when two users are trying to access same database, when the operation or transaction is done and updated at same time, there is loss of data, incorrect value for some items. So here let's take initially let's take A value as 10. Okay, initially A value was 10. Next here A is equal to A plus 10. So here it will be 110. So here write value. Now A will become 110 here, right? And on this side A value was 10, as we know, and then here we have A as 10. So 10 minus 500, 490. So here A value is written as 490. Here A value is written as 110, and here A value is written as 490. So which one would be correct? So either of them, any one of them would be selected as correct, and the other one would be discarded. But then it again leads to incorrect value of details, right? Incorrect value of data in this case or this case, it depends. Next, let's look into the next problem. So that is temporary update or dirty read. So when a transaction updates a database item but fails before completion, leaving the item in inconsistent state. So let's consider example here. T1 and T2 be two transactions. A value is read. A value is some operation is being performed here. And then again we have read of A, and then A is equal to 100 star A, and then here we have write of A, and then here we have write of A. So temporary update states that here initially we took A value as 10, and then A is equal to 100 plus A, that is 100 plus 10 is 110. So this here A value is 110. Now on this side, at the same time interval, the next time interval, A is being read. So this A won't be considered, this A would be considered. 110 is read. Okay. And here A is equal to 100 star A. So 100 into 110. So this would be the A value. Now here A is being read. So initially when A is read here, we get this value. And again when A is read, there would be a different value because A value has changed here, right? So that's what temporary update states. Then we have incorrect summary. Incorrect summary could also be explained using this particular example. Actually, it had to be 110 here when we write the value here. But then we have got 11 and 3 zeros. So we have obtained incorrect summary here. And then we have unrepeatable read. So transactions read same item again and get two different value as it was modified in between two reads. So that's what this is. So this is also the same. With using one example, it has multiple problems depending on the scenarios. So I have tried to explain all these three with one example. In exam also, they expect us to draw one particular diagram of two transactions and explain all the problems. So this was about problems about concurrency control. Now we'll look into why recovery is necessary. So in order to restore the consistent state after failures, we need recovery. Yes. So the failures could be computer failure or physical failure. Computer failure means there could be system crash, that is, there could be hardware problems, or there could be software bug, or any network issue, or any network error. That's what computer failure refers to. Then we have physical problems. Physical problems could be the transaction or system failure, that is by integer overflow or division by zero or logical problem error, or it could be logical error or exception conditions which are detected by the transaction, or there could be disk failure condition also. So in exam they can ask what are the types of failures, how do you overcome those failures. So you should write these 4-5 failures which I've mentioned, and then write these the recovery techniques. So intermediate update, immediate update, write ahead logging, shadow paging, checkpointing, and rollback, roll forward are the recovery techniques. So for details, to get to know this in detail, you can refer the PDF which I have uploaded in the Google Drive. Next, coming to schedules. So a schedule S of transaction T1, T2 till Tn transactions is considered to be total ordering or mean that for any two operations in schedule, one must occur before the other. Schedule means you're arranging the transactions in a sequential order. That is, first T1 should go, then T2 should go, then T3 should go, and so on. So if that chronological order is followed, then it is said to be serial, because they are serially occurring. First T1, then T2, T1 T2, or T2 T1, like that. If it's non-serial, then T1 T2, T1 T2, there could be like this, like how I've explained in this condition. They are not consistent here. First it was in T1 state, then T2 state, then T1, then T2. So this is non-serial. Now we'll look into what serializability is and how can it be ensured. Do you need to restrict concurrent execution of transactions to ensure serializability? So understanding the definition of serializability, it is a concept in database management that ensures transactions are executed in a way that maintains consistency and integrity of database. So serializability is a concept which makes sure that the database is consistent and integrity is maintained. So it guarantees that final state of database is same if transactions were executed serially, one after the other, even if they are executed concurrently. So even if you execute the transaction concurrently, the final state should be as though you have executed it serially. So that's what this says. So, but there's a difference between being serial and being serializable. So yeah, for serializable, you make use of concurrent instructions, and for serial, you just use the normal ordering of T1 or T2 or T2 or T1. So that's the difference. To ensure serializability, database uses concurrency control mechanisms. So this could be asked. So there are two mechanisms: usage of locks and timestamps. So in usage of locks, transaction acquires lock on data items and prevents other transactions from accessing it. So by this, that particular data item would be stored for that particular transaction. So if A is stored for T1, T2 cannot access it because it is locked for T1. So that's what acquire locks mean. So in timestamp ordering, each transaction is assigned unique timestamp based on when it started or sequential order. So transactions are then executed based on their timestamps, ensuring that they are serialized in consistent order. So next question we have, that is execution of transaction to ensure serializability. Do we need to restrict concurrent executions? So the answer is concurrency control mechanisms ensure serializability without completely restricting the concurrent executions of transactions. But the execution of transactions can still run concurrently, but their execution is controlled, and ensure that a final state is equivalent to a serial execution of transaction. So that was about serializability. This could be asked for 4 marks or 5 marks. Next, moving on, we have transactional support in SQL. So a single SQL statement is considered to be atomic. We know that. So with SQL, there is no explicit begin transaction statement, right? So whatever is there is by using the commands. You don't write hash include stdio.h or main or anything to begin the procedure. You just make use of commands. So the starting is done by writing particular SQL commands or statements. So these characteristics are specified by a set transaction statement in SQL. The characteristics are access mode, diagnostic area size, and isolation level. So access mode has two parts, that is read only and read write. And if transaction executes at lower isolation level than serializable, there could be three violations, that is dirty read, non-repeatable read, and phantoms. We have discussed these in the problems here, right? Yeah. So isolation levels control how the transaction should interact with each other. So that's what isolation level refers to. But here transaction control commands are of these types, that is begin transaction, commit, rollback, and save point. Begin is to initiate the transaction. Commit is once the transaction is completed, you need to save it. So yeah, that's what commit refers to. Rollback is, so if there's any error, you need to roll back to the initial point. So whatever changes are being made should be nullified or should be rolled back. And then we have save point. So till a certain extent, till a point in the transaction, you need to save it. Beyond that, it need not be saved. So that's what save point says. So here we have isolation levels, the types here. That is, first is read uncommitted. Read the data that has been modified but not yet committed. So this reminds us of dirty read situation, right? So that, yeah, so the problem here is dirty read will occur. Then in read committed, we read the data that has been modified and committed. So non-replaceable reads are occurring here. In repeatable read, we ensure transaction to see a consistent snapshot data throughout execution. So this is also not possible. Next, coming to serializable, highest level of isolation by ensuring transactions are executed serially. So by ensuring that the isolation levels are serializable, we can avoid all these violations. So that's what I have depicted in this table. So yeah, this is pretty easy to understand. Next, we have deadlocks topic. So how does deadlock and starvation occur? How do you resolve those? So this could be asked for 8 marks also, because it's a theory topic and you need to write for this. So deadlock occurs when each transaction T in a set of 2 or more transactions is waiting for same item. So T1 is waiting for X and T2 is waiting for Y. But then T1 has Y and T2 has X. T1 has acquired Y and is waiting for X. T2 has acquired X and is waiting for Y. In this condition, both are waiting for something and both have acquired something, right? So they'll keep on waiting. So that leads to starvation. So that's how that's how deadlock and starvation happens. So, but because the other transaction is also waiting, it will never release the lock. So this was it. So let's consider this example. So we have T1 and T2 transactions. First you read the lock Y and then you read an item Y. So Y item is stored for T1 transaction. Now here read lock X, read item X. For T1 we have Y and for T2 we have X. Now here Y wants X. Y wants to acquire the data value of X, and T1 wants to acquire the value of X and T2 wants to acquire the value of Y. But then it won't happen because T1 is in waiting queue for X, which is locked by T2 dash, and T2 dash is in waiting queue for Y, which is acquired by T1 dash. So in this condition, deadlock occurs. So deadlock prevention protocols. So it is necessary to prevent deadlocks and starvation because redundancy, right? So your particular process or particular operation or transaction will not complete at all if it is in deadlock state. So deadlock should be prevented. So it aims to mitigate the occurrence of deadlocks in DBS, database system. So we have two methods here. We have 3 methods here actually. Yeah. First one is two-phase locking. So we make use of two phases in this. That is to require transactions to lock all items they need in advance. And if any item can be obtained, none of the items are locked. So not only practical, it is not always practical due to potential resource wastage. Then we have decision-making protocols. In this, decision is made what action to take when deadlock is detected. So the options here could be to block or to abort or to preempt or to abort another transaction. So if deadlock is occurring at T1 because of T2, you have options to either delete this or abort this or preempt this or block this. So yeah, it all depends on the decision-making protocols. Next we have transaction timestamps. So as we had discussed in the previous question about timestamps are assigned to each transaction. So based on the order in which transactions are started, unique identifier or a number would be allotted to them. So if transaction T1 starts before T2, then transaction of T1 is lesser than transaction of T2. So T1 is old here and T2 is young here. Right. So the rules followed by these schemas are, first is wait and die. That is, if T1 is older than T2, then T1 is allowed to wait. Else, T1 is younger than T2, then you need to abort T1, that is, die T1. So T1 can either wait or T1 has to wait or abort in this particular situation. So once you abort, you need to restart it with same timestamp. That was about wait and die. Now we have a wound wait. So in this, the same condition, if T1 is older than T2, abort T2, T1 wounds T2, and restart it later with same timestamp. Else, here T1 was older than T2, right? Here T1 is younger than T2, then T1 is allowed to wait. Either T1 is wound, that is it aborts T2, or it waits. So if T1 is younger, if T1 is older, then it is wound. If T1 is younger, then it has to wait. So that was about wound and wait. Coming to cautious waiting, if T2 is not blocked, that is not waiting for some other locked item, then T1 is blocked and allowed to wait. Else abort T1. And then we have time bound. So within a particular duration, if that particular transaction is not getting completed, then abort it. So that's about time bound. So it is an alternative approach to manage the deadlocks, where we can check if deadlock state exists in the system or not. This is useful only when transactions have rare access to same items simultaneously. So it has to be a short transaction, lock only a few items, and transaction load is light. For heavy loads, deadlock prevention should be used. So in deadlock detection, we make use of wait for graph. So in this, the nodes represent transaction, and we need to identify the cycles. If cycles are found, that says that deadlock has been detected. So this is an example for deadlock detection. So this was about deadlock detection topic. Now we'll look into the two-phase locking protocol. So yeah, so two-phase locking protocol is a concurrency control mechanism. So it comprises of two phases. So the two phases are growing or expanding phase, and the other one is called as shrinking phase. So a transaction is set to follow two-phase locking protocol if all locking operations, that is acquiring lock, precede the first unlock operation in the transaction. So here, as we discussed, there are two phases. So the first phase is called as growing phase. So in the growing phase, transaction can acquire lock on the data items, but can't release the lock. Growing means it can acquire locks. It can acquire locks and it can't release any locks. So it keeps on acquiring locks until it reaches a point where it requests, but then there are no further locks. So in shrinking phase, once transaction has acquired all the locks it needs, it enters shrinking phase. So when locks are released, so in shrinking phase, all the locks are released that it had acquired in the growing phase. So no new locks are acquired here. So two-phase locking has a common point called lock point. So it's called as lock point, where after lock point, it can acquire and start to release. So this was in the growing phase and this is in the shrinking phase. If you look at this graph, here we have time graph. So initially we acquire the locks, right? Starts growing, we acquire the locks. Once we reach the position of lock point, all the operations are performed here. It is called as locked phase. And then after that, we keep on releasing the locks. That is releasing the locks. That's called as shrinking phase. So this is about two-phase locking protocol. Now let's look into an example here. So two transactions are there, T1 and T2. So L is to lock the item, data is A here, R is to read and W is to write, and UL is to unlock. So all lock operations precede unlock operations. So first in transaction 1, we lock A and then read A, perform an operation and then write A. Lock A, write A, perform an operation on A, and then lock A, read A, perform an operation and then write A. After writing A, you need to unlock A, right? Yeah. So after that, you have unlock A here. And then on this side, we have L, that is lock B and then read B, operation on B, write B and unlock B. So here, if you see, first unlock after completion of lock resources. So that's what has happened here. The same example here also in L2, lock item A, read item A, and then perform an operation on A, write A. And then before unlocking, you should lock another item, that is B. We have locked B here. And then we have unlocked A, lock A, unlock A. One transaction has completed here. And again, for the transaction of B, it takes place accordingly. So here there are variations of two-phase locking system. It's not that important. So the variations are static two-phase locking system, strict and rigorous. So in static, so the deadlock, it is deadlock free. After commit, we release the lock in static one. In strict, it is exclusive lock, can't be released commit until commit occurs. So deadlock may occur here. Next, moving on to rigorous, here deadlock does not occur. Deadlock may occur. The shared and exclusive locks are used here. So a lock can't be released until commit. Yeah. So now there's a question that does two-phase locking system provide serializability, like we have seen in the serializability question, right? So yes, two-phase locking protocol guarantees serializability. Serializability is execution of transaction produces same result as if they were executed sequentially, preserving database consistency, and it also prevents deadlocks and ensures consistency. So this was about two-phase locking system. Now we'll look into the Aries algorithm. So I'm not sure if this is in our syllabus or not, because many of the subscribers are telling me that this topic is not included in the syllabus, but then we had this for internal, so I'm not sure about it. So Aries stands for Algorithm for Recovery and Isolation Exploitation Semantics. So it is a recovery algorithm to provide atomicity and durability of transactions. So it ensures that the transactions are either fully committed or fully rolled back in an event of failure. So Aries recovery involves three phases. One is analysis phase, redo, and undo phase. So if in the analysis phase, so it tells which transaction to do, which pages are dirty, so the disk version not updated at the time of crash. So yeah, LSN from which redo should start, and redo log, undo log are taken care of in the analysis phase. Then coming to redo phase, it repeats history. Read as allocation action recorded in the redo log brings database to a state reflecting all committed changes that were active at the time of failure. Then in the undo phase, it rolls back to the incomplete transaction whose abort was complete are not undone here. So this was about the three phases. Looking into the features, so first feature is recovery independence. So pages can be recovered independent of others. Then we have save points. So transaction can record save point and roll back to it, which is useful in complex transactions. So every log has a log sequence number, LSN. It's called LSN. And then we make use of transaction table, which has entry of active transactions. Then we have dirty page table, which is dirty pages in buffer, which holds a record of dirty pages in buffer. Then we have checkpointing. So it records current status of database, flushing all modified data pages to disk and writing checkpoint record. So this was about the features. Now let's look into an example. So consider two transactions T1 and T2 and two data item A and B. T1 updates A, T2 updates B, T1 updates B, checkpoint occurs, T2 commits, system crashes before T1 commits. So here T1 updates data item A and B, and then T2 updates data item B. T2 updates data item B. Next is a checkpoint occurs, that is flushing all data pages to the disk and writing checkpoint record to redo log to indicate completion of checkpoint. So this is done, and after that the values are stored in the disk by the checkpoint. Now T1 was active, T2 is committed, not written. That is reapplies changes made by the T2 because their system crashes occurred here. So it reapplies changes made by the T2, that is redo log, and undoes changes made by the T1, that is undo log, and then rolls back update to B by T1. It goes back to here. So in case crash occurs here, this much data would be stored in the save point. It would be stored in the disk by the save point. That's what Aries algorithm speaks about. So after recovery, the database is consistent, reflecting the committed changes up to a point of failure, undoing the changes made by the incomplete transaction. So that's how the data is preserved. So next, moving on to the definitions. So this could be asked for 1 or 2 marks each. We have redo. So it restores the value of data items which are updated by any transaction. Yes, that is, we know that. And it is used to roll back or undo the changes made by the transactions that was not committed at the time of failure. So recovery technique that uses undo include rollback segments. That is, database maintains rollback segments, which are dedicated areas of disk space used to store before images of change data blocks. So during recovery, these are used to undo changes made by the incomplete transaction. Then we have redo. So set of values of data items updated by transaction Ti to new value. So reapply or redo the changes made by the committed transaction that were not yet returned during the time of failure. So here recovery technique that uses redo is write ahead logging. So in this, DBMS ensures that log records from transactions are written to the storage before corresponding data pages are modified. So before the modification only it is made to write. So this helps to getting back the consistent state in case of any failures being occurred. Then we have concurrency control problems that arise in multi-user database environment lead to database inconsistency, loss of updates, etc. Here we have lost update, that is WW conflict. Here, when two or more transactions attempt to update same data at same time, one of the update is lost or overwritten by another. We have seen this in the transaction topic, right? So yeah, arises when there is no coordination access to share data, leading to conflicts. Value of database is incorrect. So this is the same example which I had explained previously. So next we have dirty read. This is I have explained this also. Then we have blind write. So blind write is transaction writes data without first checking whether any transaction has already modified the same data or not. So B has written back B plus 20 here, but then here B is equal to B star 50. The value of B has changed. So that's what blind write refers to. So I have tried covering all the important questions of this module. I've tried covering all the important questions of 5th module. So I would suggest you to go through the PDF ones. The topics which I have left are pretty easy ones, and they may or may not be asked in the exam. So to be in a safer side, I would suggest you to go through the PDF. And the notes for this module would be in the description and would be in the comments. So subscribe to my channel. In the upcoming videos, I'll be updating answers for the other modules. I have uploaded answers of 1st module, 4th module, and this is the 5th module which I'll be uploading. 2 and 3 would be uploaded soon. So stay tuned, subscribe to my channel. Thank you.